An oscilloscope is probably the most useful, most general purpose of all electrical measurement systems. Oscilloscopes display voltages as a function of time. Most other devices used in measurement of electrical signals, such as voltmeters, provide a single number which supposedly characterizes a signal. An oscilloscope, however, allows the user to view the time-varying function directly, so that no assumptions need to be made as to the actual signal shape. By examining the waveform displayed by an oscilloscope, the user can typically identify DC components, the shape of any time-varying waveforms, and noise. This allows the user to interpret the data without making unwarranted assumptions. This is a representation of the connectors on your Analog Discovery. The Analog Discovery Oscilloscope has the capability of measuring two different voltages, channel 1 and channel 2. Like the voltmeter instrument, each channel requires two connections, since we're measuring a difference in voltage between 2 points. The channel 1 connectors are 1 plus and 1 minus, and the channel 2 connectors are 2 plus and 2 minus. In fact, the oscilloscope and the voltmeter share the same connectors, so only one of these instruments can access the connectors at any given time. On the Analog Discovery, the 1 plus terminal is connected to an orange wire, and the 1 minus terminal is connected to an orange wire with a white stripe. Likewise, the 2 plus terminal is connected to a blue wire, and the 2 minus terminal is connected to a blue wire with a white stripe. To demonstrate use of the oscilloscope, we'll measure voltages in this simple circuit. The power supply will apply a time-varying voltage to the circuit, and we'll use channel 1 of the oscilloscope to measure the resistor's voltage difference and channel 2 to measure the diode's voltage difference. This is the circuit we created in the WaveGen instrument Quickstart video. The applied voltage is from channel 1 of the arbitrary waveform generator. We're using channel 1, the 2 orange wires, to measure the voltage across the resistor, and channel 2, the 2 blue wires, to measure the voltage across the LED. Now we're ready to apply power and test our circuit. We'll use the WaveGen instrument to apply a low-frequency triangular voltage wave to the circuit. Let's make the frequency of the triangle wave 1.3 Hertz and its amplitude 3 volts. Click on Run AWG1 to apply power to the circuit. As expected, the diode lights up when the voltage across the diode exceeds about 2 volts. This condition occurs about 1.3 times per second. Now let's use our oscilloscope to display the resistor and diode voltages. To open the oscilloscope, simply click on the scope icon on the waveform's main window. The Analog Discovery Oscilloscope has a large number of features, so its interface is fairly complex. In this tutorial, we'll present the most basic use of the oscilloscope. In order to start acquiring and displaying data, click on the Run button on the oscilloscope window. To stop acquiring data, of course, click Stop. The data as a function of time is displayed in the main window. The horizontal axis of the main window is time, and the vertical axis is voltage. Notice that our time scale, at least, isn't well suited to the data we're collecting. We're only seeing 10 milliseconds, or 1/100th of a second, worth of data on the screen at any time. Since the waveform we're applying is changing pretty slowly, we're seeing only a small portion of the waveform in the screen at any given time. The overall effect is that we're seeing a series of sequential snapshots of the data. We can control the time axis with the time control box on the right side of the window. 200 milliseconds per division, for example, provides a pretty good representation of the signal, without it taking overly long to fill up the screen. We can change the way the data is presented, by the way. By default, if the time base is high, or if the window shows a long time frame, the data scrolls past the window. Once it gets to the right edge of the window, it starts over again at the left side of the window, erasing the previous frame of data as it goes. You can modify the way this data is displayed if you want to. Select View in the menu bar and click on Advanced Trigger. This will cause some additional options to appear in the available tools. By default, in the Run options, Screen is displayed. Let's change this to Shift. The main window will now shift to follow the waveform. Once the waveform reaches the right side of the window, the waveform will slide to the left so that the new data points always appear at the right-hand side of the screen. If we select Repeat in the Run options, the oscilloscope will display one window's worth of data at a time. The window of data is refreshed all at once. when the entire data set is acquired. We're seeing snapshots of the data in the main window. If the time base is low, less than 100 milliseconds per division, the oscilloscope always displays the data in repeat mode. This is because most humans cannot interpret data which is scrolling past them very rapidly. As we saw above, in screen mode, the oscilloscope displays frames of data, much in the way a movie is composed of static picture frames which are successively displayed to give the impression of movement. The trick with this data display, of course, is to make the successive pictures coalesce to create a coherent display. On an oscilloscope, this is usually done by setting what is called a trigger. Triggering allows us to assign a zero time to a particular feature on the signal. That feature gets placed on the same point on the plot window every time the oscilloscope screen updates. If the signal repeats itself based on that feature, the oscilloscope will display the same section of the signal every time the screen updates, making it appear that the signal isn't changing. In this demonstration, we won't use any advanced trigger options, so I'll turn them off again so they don't distract us. The trigger point corresponds to a set of conditions which the scope will look for in your signal. A typical trigger point is defined by a voltage level and a slope condition. The voltage level is fairly self-explanatory. It's simply the value of voltage at which the trigger condition occurs. The slope condition defines whether the trigger point is set based on the signal increasing, called a rising edge trigger, or decreasing, called a falling edge trigger. The trigger source also needs to be defined. We will use either channel 1 or channel 2 as the source of our trigger signal. Let's use the trigger to try to help us view our data. We'll trigger off of channel 2. Arbitrarily, we'll set the trigger level to 1 volt and trigger on the rising edge. Notice that the defined feature, a 1 volt level, while the voltage is increasing, now lines up with 0 time on the main window. Every frame of data lines these points up at 0. Since the signal repeats itself at regular intervals, the successive frames give the impression that the waveform isn't changing at all. Now it's easy to make measurements. We can also change our trigger level by clicking and dragging the triangle at the right of the screen. And we can change the location of 0 time by clicking and dragging on the black triangle at the top of the screen. We can also change the condition to falling so that the signal triggers while the voltage is decreasing. We've now talked about setting up the time axis to display the waveforms. Now let's talk about the options that allow us to modify the vertical axis and the displayed data channels themselves. Each channel of data has its own control box on the right-hand side of the screen. The control box allows you to set a vertical scale, or range, in volts per division, and an offset in volts for that data channel. The vertical scale displayed on the window is for the selected data channel. It's color-coded to emphasize which channel it corresponds to. You can select a channel of data by clicking on the waveform itself or on the tab at the top left of the main window. If you want, you can also change the offset of the data by dragging the triangle at the left side of the window, or left-clicking with your mouse on the vertical scale and dragging. The range can also be set by right-clicking on the vertical scale with your mouse and dragging. If you don't want to display a particular channel on the oscilloscope main window, simply disable it by unselecting the check mark on the box next to the channel name in its controls. So far, we've only talked about continuous data acquisition. The data is always being acquired as long as the Run button has been clicked. Sometimes, we want to acquire only a single window worth of data. We'll use this piezoelectric sensor to illustrate use of single sequence acquisition. Our piezoelectric sensor outputs a voltage difference between its terminals when it's bent. These sensors are often used in vibration measurement. We've inserted the terminals of our sensor into 2 holes in our breadboard and connected the channel 1 probes of the oscilloscope to the terminals so that we can measure the voltage output of the sensor. When we measure our sensor's response, we'll start out with a long time scale and use continuous acquisition to examine our data. Every time we flick the sensor, we see a response on the measured voltage. Unfortunately, at this time scale, we can't tell much about the signal. We can reduce the time base, but it's now rather haphazard as to whether we see our signal or not. Setting a trigger will help, but the data gets reacquired every time the trigger condition is met. If we want to take a snapshot of the waveform, which won't get replaced without our permission, we can use the single button to acquire a single set of data. This also requires us to set a trigger since the data is acquired based on the trigger condition being met. We've already set an appropriate trigger, so that step's complete. Notice that the status box claims it's armed. This means that the trigger condition is set and the scope is waiting for the condition to be met so that data acquisition can start. If we now flick the sensor, the condition is met and the data acquired and the status is done. Once the entire window of data is acquired, it's displayed and held. The data remains in the window until another request to acquire data is received. Now we can use our oscilloscope to measure and display time-varying waveforms. We can determine parameters we want to directly from the main window, of course, but sometimes it's a little bit tedious to make these measurements ourselves. There are a few tools available that can make our lives easier in this respect. Clicking on the Measure button opens a measurement window. This window displays a number of different measurement possibilities. You can choose the measurements you want to make. Those measurements will automatically be displayed in the measurement window. Likewise, information relative to specific points on the waveform can be obtained using the cursors. These types of tools make it easy to make measurements, but should not be relied on entirely. Always examine the actual waveform shape in the main window. That's the only way you can determine whether the measurement you're making is appropriate.